since the left side is more complicated, so we begin with this left side. So L. And fourth, let's try to factor this numerator. So this, if you use the substitution, this is the x squared plus x minus 2, right? So x squared plus x minus 2. So let x be this sine beta. And we know how to factor this polynomial. This is equal to x plus 2 times x minus 1. So now you can do the back substitution. Then you get sine beta plus 2 times sine beta minus 1. And the denominator, we can also do this factoring. So we can factor out this 2 times sine beta minus 1. Okay. Now you can cancel the common factor. So this cancel, and then you have the sine beta plus 2 over 2. And this is the right side. And then we know this is identity. Done. Now let's look at one more problem about the identity. So let's look at the 93. So sometimes if the both sides are equally complicated and you don't know which side to begin with, then you can always try this method. Just use the left side minus right side and prove this difference is equal to 0. So now this 93, we will use this method to prove this is identity. So let's go to the page 525, problem 93. So the left side, okay, let me first write this identity. We need to prove, okay, natural log of the absolute value of the secant alpha plus tangent alpha equal to negative natural log of the secant alpha minus tangent alpha. And let's get the left side minus the right side. So this is just equal to natural log of the absolute value of the secant alpha plus the tangent alpha, and plus natural log of the secant alpha minus tangent alpha. Okay. And by the property of the logs, we know the sum of the logs is equal to the log of the product of these two inputs, right? So we have the natural log of the product of the absolute value of the secant alpha plus tangent alpha and the absolute value of the secant alpha minus tangent alpha. Now you can put these two facts together, just use one pair of the absolute value bars. So you have the absolute value of the secant alpha plus tangent alpha times secant alpha minus tangent alpha and the absolute value. Then here this is a plus b times a minus b, right? So you have the a squared minus b squared. So that is a secant square alpha minus tangent square alpha and the absolute value. And by the one of the Pythagorean identities, we know this secant square alpha minus tangent square alpha is equal to 1. So this is just equal to the absolute value of 1. Right? And this is the natural log of 1. We know the log of 1 is always equal to 0, right? So this guy is equal to 0. So this just implies L minus R is equal to 0. So we have the L equal to R. So in this way, we verify this is really identity. Done. Now let's look at the section 3. So let's go to the page 535 and let's look at the problem 28. We need to simplify this expression by using sum or difference identities. So let's copy this problem on the whiteboard. Tangent of 5 pi over 12 minus tangent of pi over 12 divided by 1 plus tangent of 5 pi over 12 times tangent of pi over 12. Tell me which identity should I use? Which one? Identity of sum or difference? Sum or difference? Difference of what function? Tangent, right? So let's record the tangent of a difference identity. So you have the tangent of alpha minus beta equal to tangent alpha minus tangent beta of 1 plus tangent alpha times tangent beta. Okay. So now by applying this identity, we have this expression equal to tangent, and this 5 pi over 12 is alpha, and this pi over 12 is beta. So you have the tangent of the 5 pi over 12 minus pi over 12. And then you simplify, you have the tangent of the 4 pi over 12. And this is equal to tangent of the pi over 3. And what is the value of the tangent of the pi over 3? What is this value? Root of 3, right? Root of 3. Then done. Now let's look at the 39. Use appropriate identities to find the exact value of this expression. Okay, don't use a calculator. So we need to find the tangent of the 75 degrees.